Good morning, our dear listeners, and welcome to today's class. Today, we will be discussing with you in details the idea of independent events in probability. Independent events. Independent events. What do we mean by independent events? When do we say events A and B are independent? Events A and B are independent. We say that events A and B are independent if and only if the knowledge of the occurrence of any of them does not affect the chance or the probability of the occurrence of the other. It happens that way we say events A and B are independent. Let us to also look at it from another dimension. And of course, a very closer approach to what is meant by independent events as it concerns events A and B. Events A and B are said to be independent if and only if the knowledge of the occurrence of event B does not affect the chance or the probability of the occurrence of what of event A. And this explanation I gave this way can be expressed this way. That the probability of occurrence of event what A, given the information that event B already had happened, is given as what? Probability of what? Event what? A. I explained. That is to say that even though we are aware that event B earlier had happened, the probability of event A happening was not altered, it was not changed, it still remained probability of what? Event A. That is to say that under independent events, the conditional probability of event A happening, given that event B earlier had happened, returns back the probability of event A. The same thing applies with event B, that A and B are said to be independent if and only if the knowledge that event A earlier had happened does not change the chance or the probability of the occurrence of what? Of event B. And equally, this explanation can be expressed as that the probability of event B happening, given the information that event A earlier had happened, is given as what? Probability of what? Event what? B. That is to say that even though we have the information, we are aware that event A earlier had happened. The probability of event B happening was not altered or changed by the occurrence of event A earlier. It is still returned what? Probability of what? Event B. That is, this event B here did not affect the probability of event A. It returned probability of event A. That is, probability of this event A happening earlier did not affect the probability of this B as occurring. It is still returned what? Probability of what? Event B. And we are told that if this and this are true in probability, it implies that probability of A intersection what? B is given as probability of A multiplied by probability of what? B. That is, that if A and B earlier had been declared independent, it implies that the joint occurrence of events A and B returns the product of the probabilities of the individual events A and B. If this condition holds, and if this condition holds, and if this condition holds, we categorically say that events A and B are independent. How do we give a real life illustration of independent events? Consider the first toss of a fair coin and the second toss of what is a fair what? Coin. The first toss and then the second what? Toss of a fair coin. And of course, you know that the outcome of the first toss is going to be, it is either what? Head or it is what? Tail. Here equally, it is either what? Head or it is what? A tail. These are only two possibilities you can have when you toss a single coin up. You can either get a head or you get what? A tail. Now let us say that we have event what? A, where this event A is talking about obtaining head in the first what? Toss. Let us also have event what? B, where we say that this event B stands for obtaining what? Head in the second what? Toss. You find out that the occurrence of a head in the first toss of a fair coin does not affect the chance of a head coming up in the second toss of what? That a coin. Therefore, event A here, which is head, and event B here, which is head, are independent events. The same thing applies when the two fair coins are tossed up together. The occurrence of head in the first what? Coin does not affect the occurrence of what? Head in the second what? Coin. If it happens that way, we now say that event what? A and B are independent event. Simply because the occurrence of one in a particular what? A fair coin does not affect the occurrence of that same thing in another coin. It happens that way, we now say A and B are independent. Consider also the toss of what? A fair die. The first toss of a fair die, and then the second toss of a fair die. And of course, a fair die contains what? 6 possible outcomes. And those 6 possible outcomes, here's 1, I have 2, I have 3, I have 4, down to 6. Here 1, here 2, 3, down to what? To 6. You find out that if event A here is talking about obtaining what? 3. And event B here is equally talking about obtaining what? 3. You know quite alright that the occurrence of what? 3 in the first toss of what? A fair die does not stop or change or alter the chances of 3 occurring in the second what? Die. And if this A is the chance of what? The event of getting 3 here, and this B here is a chance of getting 3 in the second what? Die. It implies that event A here and event B here are independent because none affects the chance or the probability of the occurrence of the other. These are little real-life illustrations that can portray or expand your knowledge on independent events. Actually, the focus of our class today is to go about driving some conditions or establishing some conditions or reaffirming conditions that earlier had been stated that if events A and B are declared independent, that those following conditions will hold. So we are going to clean the board. Beginning from this one, they say it is true. That if this is true and this is true, this what implies. We are going to show how this implies. So permit me to clean the board while we now look at those conditions that the A and B must satisfy if they are independent events. So permit me to clean here. Talk about conditions. Talk about what? Conditions. that A and B must satisfy if this A and B are two events that are independent of each other. Number one, they say that probability of A intersection what? B is given as probability of A multiplied by probability of B. How do we establish this? That in independent events, this is true. We now see solution. Remember, of course, that by definition, by what? Definition, we have the probability of what? A giving what? B equals probability of what? A. If this A and B are independent. We stated this earlier. So do remember this. And of course, I want to recall for you the definition of a conditional probability. The definition of a conditional probability says that the conditional probability is the ratio of the joint probabilities of the events involved all over the probability of the event that happened there earlier. Therefore, if I write probability of A giving what? B, in terms of conditional probability, it is going to be the ratio of the joint probability of A and B all over the probability of the event that happened earlier, which of course here it is what? It is B. And do remember that when we talk about joint events or joint probability in sets, we are talking about the probability of the intersection. Therefore, this can be expressed as probability of what? A intersection what? B, all over probability of what? B. That is to say that in conditional probability, it is expressed as the joint probability of A and B all over the probability of the event that happened earlier, which of course is this what? B. And of course, you know I can say all over what? 1. And when I say all over 1, I cross multiply. By saying 1 multiplied by this will now tell me that P of what? A intersection what? B is given as. This will multiply this, which means I have that P of A giving what? B multiplied by P of what? Of B. But then earlier on, we earlier had defined here that the probability of A giving B is given as probability of A because A and B are said to be independent. And our intention is to establish that if A and B are independent, that this condition holds. We have arrived here. What I have here is what I have here. Then I come over here. And I want us to look. P of A given B had been given as what? P of A. So I will now say but. P of what? A giving what? B equals what? P of what? Of A. According to the definition. According to this what? Definition. When I say therefore, what I have here is P of what? A intersection what? B is given as P of, in place of P of A given B, I'll write what? P of what? A, which is this, multiplied by what I have is what? P of what? B, and it is established that in independent events, as it concerns A and B, that the probability of their intersection equals the product of the probabilities of the individual events. This is true. So we now move down. We believe that nothing is confusing thus far. You are told that A and B are independent. You have information. And you are told to show that this is equal to this. Beautiful. Because A and B are independent, it implies that the knowledge of B occurring does not affect the probability of what A occurring. And that was what led us to this definition. That the probability of A given B is the same thing as probability of what? Of A, according to definition. of independent events. Then we progress. We record for us ourselves that ordinarily in conditional probability, that the probability of A given that B earlier had occurred is defined as the ratio of the probability of the intersection to the probability of the event that happened earlier, which is this all over what this. By a word of cross multiplying, I have 1 here. 1 multiplied by this will give me this, which returns what I have here. Then this multiplied by this will now return what I have here. But then looking at A, probability of A given B, which was earlier declared as what? P of A. It means that in place of P of what A given B, I can replace with what? P of what A. And that was what led me that in place of this P of A given B, this is P of A. Multiplied by, here is what? P of what? Of B. So it has been established that in independent events, that if A and B are independent events, that this condition what holds. Thank you very much for your audience. Permit me to clean it now while we go over to the second condition. We are going to do it up to 3 conditions. So permit me to clean this one. We are told that is number 2. They said, and I write, that if A and B are independent events, or put this way, that if A is independent of what? Of B, it implies that equally B is independent of what? Of A. That's what they said. That if A is independent of B, it implies that B is independent of what? Of A. How do we establish that? The only thing we know here is that they have told us that A is independent of what? B. Which makes us now to write that what? P of what? Of A given what? B is equals what? P of what? Of A. That's one thing we know for sure now. And of course, we know as well that this thing can equally be written this way. That probability of what? A given what? B is given as probability of A intersection what? What? B all over probability of what? Of B. Using the idea of what we call conditional probability. And if that is true, it implies that I am going to say that this is all over 1 as usual. This goes into this. I have therefore, this goes into this. I have therefore that P of A intersection B is given as, when this multiplied by this, I have P of what? A given what? B multiplied by P of what? Of B. And of course, you know that according to definition still, we have that this is what? P of A. So I will still say, therefore, that my P of A intersection, what? B is given as P of A multiplied by P of what? Of B. This was what we established earlier, but that is not where we are going. We want to establish that if A is independent of B, B should be independent of what? A. So in that case, I am now going to say but. I say but. Probability of what? B given what? A is defined as, according to the definition of a conditional probability, this is going to be the ratio of P of A intersection what? B all over what? P of the event that happened earlier, which is what? A. Which is what? A. But do you know that we are already aware that the probability of A intersection B is given as this, P of A intersection B, and it is defined as this quantity. So what I'm going to do that the numerator says P of A intersection B, in place of this numerator, I am going to go with P of A multiplied by P of B because they are the same thing. So I say that this implies now that P of what? A multiplied by P of what? B all over what? P of what? Of A. Which is what I have at the denominator. Here is P of A, here is P of A. They can go. So this and this is gone. You now say, therefore, that P of this B given what? A is given R. What is remaining here is what? P of what? Of B. And this proof establishes that B equally is independent of what? Of A. Because what this thing means is that even though we are aware that A earlier had occurred, the probability of B occurring still returns what? P of B. So the information or the knowledge of this A occurring earlier didn't affect, alter, or change the magnitude of the probability of occurrence of what? Of B. It is still returns what? P of B. So this proof establishes that if A is independent of B, B should be independent of what? Of A. This is the second condition. And I kind of refreshing your mind. When they gave us A and B, they gave us an additional information that A and B are independent, that A is independent of what? Of B. That's the additional information they gave us. And they say on the grounds that A is independent of B, we should show that B equal is independent of what? Of A. We began by the one they told us, that A is independent of what? B. That was why we wrote that probability of A occurring given B should be probability of what? Of A. Because this event B occurring earlier will not alter the probability of A occurring. That's what we have here. So we ended here. We now came over here. We said that ordinarily, relying on the definition of conditional probability, we know that the conditional probability of A given B is expressed as the ratio of the probability of the intersection of the two events to the probability of the B, which is the one that happened what? Earlier. At the end of which we now cross multiply by saying all over 1. 1 multiplied by this gave me this. This multiplied by this gave me this. But if you look at this, that's what I have here. And we have said that it is equal to what? A based on that definition. So in place of that, I will use my A multiplied by B. We already had established this one earlier in the first condition. Then we move ahead. Moving ahead here is to go and show that B should be independent of A. It means that the probability of B occurring given A. That is what I wrote here. Probability of B occurring given what? A. Based on the conditional probability should be expressed as joint probability, which is the probability of the intersection of the two events A and B, all over the probability of what? The one that happened earlier, which is what? A. That's how we arrive here. But then if you watch here, the numerator says P of A intersection B. And this is P of A intersection B that can be expressed like this. So I quickly now, in place of this numerator here, I express it now with this. All over the denominator, which is P of A. And that makes P of A to be a numerator and made P of what? B to be at the denominator, P of A. So when this P of A cancel this P of A, what is left here is what? P of what? B. And if you return here, you find out that probability of B given A is now probability of what? Of B. That is, the knowledge of A occurring earlier didn't change the probability of B occurring. It is still returns what? P of what? B. That is the second condition, which they say A and B must satisfy if A and B are independent, or if A is independent of what? Of B. B should be independent of what? Of A. That second condition is proved. We move to the third condition. So permit me to clean this. The third condition says that if A and B are independent, that A intersection B complement, or that A and B complement are equally independent. That's what they say. That condition number 3. They say A and B to being independent implies that A and B complement equally should be what? Independent. That's what they are saying. So by implication, we already know that when A and B are independent, that this is true. That P of A intersection B is given as P of A multiplied by P of what? Of B. Therefore, what we are going to prove here is that P of A intersection B what complement should be able to give us what? P of what? A multiplied by P of B complement. If this is this, this should be this. So this is what we want to prove. This is what we want to prove. And we are going to prove this thing with the use of a Venn diagram to bring out the concept of this intersection much clearer to our audience. So if you have a Venn diagram drawn this way, this is a Venn diagram drawn this way. And there are two sets inside this Venn diagram, which are represented with what? X. This Venn diagram is talking about then the sample space. So I have events and I have another event. This my event is event A, this my event is event what? B. This center here is what we call A intersection what? B. And this place alone, let me now use circle to represent that intersection. Small not, sorry. And then let me now use small good to represent the area and use small star to represent the area of B. I have already said that this intersection that contains small north is A intersection B. And this area that is contained with what? Good, small good, is this area now is A intersection B complement. Because we are removing everything that concerns what? B. So this area containing small good is A intersection B complement. So by implication, if from here to here is A intersection B complement, if I must get the complete A, which is from here to here, this is complete A. This is complete A. So if I must get the complete A, it means I am going to add A intersection B complement with A intersection B, because it is this area and this area combined that will make this what? A. By implication, A alone from that Venn diagram, A alone is given. This area that contains good is what? A intersection B complement. I will say plus. This area, this A equally contains this area that is what? A intersection B. So I have what? A intersection what? B. From this Venn diagram, the total region of A comprises the area where A doesn't share, which is this, and comprises the area where A and B share in common, which is this. So what I'm now going to do, permit me to clear what came up on my phone. So what I'm going to know that A alone is going to be the area shared alone by A plus, which is this, plus the area shared by both of them, which is this. This is what I have. I'm turning this into probability. I now have therefore that my P of A here is given as P of what? A intersection what? B complement plus what? P of A intersection what? B. Remember that we earlier had established, I will say, recall that. We earlier established that P of A intersection B is given as P of A multiplied by P of what? B. That has been established earlier. This quantity here, we have already established it. That if A intersection B, that if A and B are independent, the probability of A intersection B is expressed this way. So what I'm going to do is to return back to this formula. Wherever place I see P of A intersection B, I will replace with this quantity. And that will now make me, therefore, what do I have here? P of A. I have P of A equals. What do I have here? P of what? A intersection what? B complement. I'll close it. Permit me to remove what came up on my phone. Then instead of writing P of A intersection B, I'm going to write this. So I'll now say plus P of what? A multiplied by P of what? Of B. Permit me to clean this top so that I can continue the proof from there. This is an additional sign, so it can be brought over here. This quantity can be brought over here, and I have therefore that P of what? A, which is what I have here. This one coming over here, minus P of what? A multiplied by P of what? B is given as P of what? A intersection B complements. If you watch, there is P of A here, there is P of A here. It can be factored out. And when I factor it out, what I have is what? P of what? A, open a bracket. What will be left here is what? 1 minus. Look at the minus. What will be left here is what? P of what? B, close the bracket this way. This is given as P of A intersection B complement. And of course, anytime you have, I will not say but 1 minus P of B equals P of B complement. Anywhere we have 1 minus P of what? Of B, it is known as what? B complement. So in place of this 1 minus what? P of B, I'm going to use what? P complement. I'll say therefore P of A, which is what I have here, multiplied by, here is now going to be P of what? B complement. Is given as what? P of A intersection B complement, which is exactly what we want to show. That if A and B are independent, that A and B complements are equally independent. And how do we show it? By showing that the probability of A intersection B complement is going to be the same thing as probability of A multiplied by probability of B complement, which is what we established here. That is the term condition they gave us under these independent events. We are quickly going to take one example. We are quickly going to take one example to actually showcase what we have said so far. So permit me to clean the board and then showcase one example. Do remember that this third condition says, if A and B are independent, that A and B complement are equally independent. We should show that. But the only thing we know is that if A and B are independent, then the probability of their intersection is the product of the probabilities of their individual selves, which is A and what and B. So what we wanted to show is that if A and B complement must equally be independent, it means that the probability of A intersection B complement is going to be probability of what? A multiplied by probability of a B complement, which is what we established here. Thank you for your audience. Let us take a question first. The question says, and I write, for us to see how it goes. The question says, let A and B be two independent events. That is question number 1. Let A and B be two independent events such that probability of A is 0.2. They say such that P of A equals 0.2 and P of B equals 0.8. They ask us, Number I. Number I. He said we should find P of A intersection B. I. That we should find P of A or B. We now have I. This is I. P of what? P of B, not A. P of B, not A. So we are going to look at those things one after the other to see how we can solve this kind of question. When we are given this kind of a thing, we can only solve them correctly if and only if we have idea of the kind of event that A and B are. Luckily enough, the question already have told us that A and B are independent. So the only thing required of us is to be able to dish out conditions that we know which A and B should satisfy on this condition that A and B are independent. What is that first condition? That first condition is even what we are going to use to solve I. We either had established so as a way of solution. We either had established that P of A intersection B, when A and B are independent events, will be P of A multiplied by P of B. We already have established this. And because we have established this now implies my P of A was given as 0.2. My P of B was given as 0.8. So this becomes 0.12 multiplied by 0.18. You should either give me 0.16. That is the probability of this intersection. Then we quickly come to II. II says probability of A or B. Of course, you know that or in probability means plus. And of course, you know that the or plus in probability means what? Union. So what this thing means is you can either say P of A or B, which is the same thing as P of A plus B, which is the same thing as P of A union B. So we can use any of these things to solve this problem. And I want to recall for us the addition law of probability. Addition law of probability. The addition law of probability says, and I write, that when we have P of A union what? B, that it is the same thing as P of A plus P of what? B, minus P of A intersection B. That is what the addition law says. And this law is given independent of whether it is independent event, or whether it is a mutually exclusive event, or whether it is a dependent event, or whether it is any kind of event. This is just what we call addition law of probability. It is when they now say that your A and B are independent, you now ask yourself, okay, if A and B are independent, it implies that A intersection B can be expressed this way. And it is all on that ground that you can say that this thing becomes this P of what? A plus P of what? B minus. Instead of writing P of A intersection B, you know that P of A intersection B in independent what? Events is equal to P of A multiplied by P of B. So you have what? Minus P of what? A multiplied by P of what? Of B. And this equals. My P of A is 0.2. So you have 0.12 plus. My P of B is 0.8. You have 0.18 minus, which is this place. My P of A is 0.2. So I have what? 0.12 times 0.8. And of course, this to this will give me what? 1 or 1.0 minus. This earlier gave me 0.16. And if you say 1.0 minus this, I think it will give us a 0.84. That is 1 minus 0.16. will be able to give us 0.84, I guess. You can press your calculator to confirm that. Okay? That is for number 3. Addition law, always remember this addition law of probability. The moment you remember it now, you call up this one, so you'll be able now to know exactly where you are going. Then we now go to the last one. So permit me to quickly clean here while we go over to the third one, which they ask us to show. Okay? What we have here is P of B, not A. When they say P of B, not A, it means P intersection A complement. They don't need A. That's what they mean by that. But you do remember, let me write II. Remember, that is the third one. That the third condition we proved today is that P of A intersection B complement is given as P of what? A, open a bracket, 1 minus P of what? B. Remember, we established this one today in the third condition. That's what we established. By implication, if we are to find, because what this thing means is P of what? B intersection what? A complement. That's what this thing means. B, not A. Okay? Permit me to pause something that came up on my phone. So what this thing means is this. So by implication, this is going to be. We have that this is going to be P of what? B. In place of A here, you are going to write B. Then you now open the bracket. 1 minus P. Here is my B when I'm talking about A. So here is going to be my what? My A. So I now have my what? My A here. Close up the bracket. So this equals. P of B is what? 0.18. So you have what? 0.8 multiplied by. Here, or let me say just open a bracket. Here is what? 1 minus. P of A is 0.2. So you have what? 0.2. Close up the brackets. So this is now going to be. Here is 0.8 multiplied by 1 minus 0.2 is what? 0.8. And then this is 0.614. So you have now been able to show it. Thank you very much for your audience. And stay calm with us. We are going to continue to make effort till one day everything about mathematics and probability to you will become a topic of interest, a topic of concern with love and the rest of them. Remember that the major thing here is to discuss this concept with you in a way and manner that will be able to kill or suppress your phobia on the subject matters, mathematics and statistics. Stay put and wait for us when we are going to bring for you the knowledge of mutually exclusive events, or what we call mutually disjoint events. Thank you very much and stay tuned.